This problem involves working with the equivalent circuit for a single-phase induction motor. In order to solve this problem, you will need to understand how the equivalent circuit was developed. So, the first part of this problem will be the theory behind the development of the single-phase equivalent circuit. That's why I have broken it into several parts, beginning with number 6A. As the name suggests, these motors are used on a single-phase supply. Single-phase motors are the most familiar of all electric motors because they are extensively used in the home appliances, shops, offices, etc. It is true that a single-phase motor is less efficient than a three-phase motor, but three-phase motors are normally not available except in large commercial and industrial establishments. This has led to the development of the single-phase motor. Most single-phase induction motors have a squirrel cage rotor and a single winding on the stator. In order to study the single-phase induction motor, I'm going to take the liberty of using Tesla's induction motor patent. Not that it was patented as a single-phase entity, but only because it's simple in construction and easy to morph into a single-phase induction motor. So I will modify it to suit our needs. Single-phase induction motors suffer from a severe handicap. Since there is only one phase on the stator winding, the magnetic field in a single-phase induction motor does not rotate. Instead, it pulses, getting first larger, then smaller, but always remaining in the same direction. Because there is no rotating stator magnetic field, the single-phase induction motor has no starting torque. A single-phase induction motor is not self-starting, but requires some additional means of getting it started. The single-phase stator winding produces a magnetic field that pulsates in strength in a sinusoidal manner. The field polarity reverses after each half cycle, but the field does not rotate. Consequently, the alternating flux cannot produce rotation in the stationary squirrel cage rotor. This fact is easy to see from the examination of the motor when it's in its stationary position. The stator flux of the machine first increases, then decreases, but it always points in the same direction, plus or minus. Since the stator magnetic field does not rotate, there is no relative motion between the stator field and the bars of the rotor. Therefore, there is no induced voltage due to relative motion in the rotor, no rotor current flows due to relative motion, and no induced torque. Actually, a voltage is induced in the rotor bars by transformer action, and since the bars are short-circuited, current flows in the rotor. However, this magnetic field is lined up with the stator magnetic field, and it produces no net torque on the rotor. At stall conditions, the motor looks like a transformer with no short-circuited secondary winding. The fact that a single-phase induction motor has no intrinsic starting torque was a serious impediment to the early development of the induction motor. When induction motors were first being developed in the late 1880s and early 1890s, with the materials and techniques then available, it was impossible to build a motor that worked well. The induction motor did not become an off-the-shelf working product until three-phase power systems were developed in the mid-1890s. However, once the rotor begins to turn, an induced torque will be produced in it. If the rotor of a single-phase motor is rotated in one direction by some mechanical means, it will continue to run in that direction of rotation. As a matter of fact, the rotor quickly accelerates until it reaches a speed slightly below synchronous speed. Once the motor is running at this speed, it will continue to rotate even though single-phase current is flowing through the stator winding. This method of starting is generally not convenient for large motors. In order to study this phenomena a little closer, I'm going to spin the rotor in a counterclockwise direction very close to synchronous speed omega of the single phase supply. Assuming that it is still spinning close to synchronous speed, I'm going to take a snapshot, which essentially freezes the motion. Because the rotor bars are turning or moving, they are cutting the pulsating field such that, according to Faraday's law, a voltage will be induced in the rotor bars directly below the field poles. It will produce a voltage in one direction in the upper bars of the rotor and in the opposite polarity in the bottom bars of the rotor. I've indicated that with a plus sign and a negative sign. Because the rotor bars are shorted at each end by end plates, that induced voltage will cause current to flow into the page on the top of the rotor, returning out of the page at the bottom of the rotor. Remember, this induced current is only due to the motion of the rotor turning. According to the right-hand rule, the current will induce a magnetic field in the direction of the left, indicated by the blue arrow. Notice that the phasor is 90 degrees with respect to the stator magnetic field. At this point in the analysis, all we have established in regard to the blue magnetic field is that the direction will be to the left, and we know the red phasor direction is up or down. However, both magnetic fields are oscillating. That is to say, the stator phasor we know is oscillating up and down, while the blue phasor, which is momentarily going to the left, is also oscillating left and right. In order to look at the relative timings of these two oscillations, we need to look at them in the time domain. Let's use the stator magnetic field as a reference. It is sinusoidal and it looks like this. Because it is a reference, we're going to compare all other functions relative to it. We know that indeed, or the induced voltage in the rotor bars is due to the motion of the bars cutting the magnetic field. That voltage is described by Faraday's law, which tells us the voltage is equal to minus the change in flux field over the change in time. That means the voltage will also be sinusoidal, but it's going to be following the slope of the red curve, which means it's going to be exactly the same shape, but lagging by 90 degrees and starting out minus. Now, the current in the rotor bars is just given by Ohm's law, and the impedance is almost all resistive, so there is no phase shift between the voltage and the current, and it will look like this. The magnetic flux is instantaneously proportional to the current. Since the current is sinusoidal, this means the blue magnetic flux is going to follow the same sinusoidal wave shape. This current is what is induced in the magnetic field and will be described with the blue phasor. So we know that there are two magnetic fields in the vicinity of the rotor, and their timings will look like this. You should start to recognize this situation: two magnetic fields with the relative positioning and timings. These two magnetic fields with this relative positioning and timings, when added together, produces a rotating magnetic field, in this case in a counterclockwise direction. This means that the rotor, once started by some other means, will continue to rotate as long as the single-phase sinusoidal field is present. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure you're not left in the dark when the next storm hits. EcoFlow is having a super prime big deal days for a limited time only. Check them out at these sites: EcoFlow Canada at this web address and EcoFlow USA at this web address. You can also use coupon code 25PDFAFF to realize an extra 5% discount.